At page 87, number 1, the question is to convert into spherical coordinates, and then, the implication is that we would actually find the integral, although the question doesn't explicitly state that. All right, so the first thing that we would want to do is note that, or at least the first thing we want to consider, dx, dy, dz, whatever order, is going to be rho squared sine phi d rho d phi d theta. Yep. We'll have to swap out the x squared plus y squared plus z squared. We'll take care of that in a sec. And then, well, actually, we can take care of that now. That's easy enough because it's right here. I'll highlight that for you. This relationship, rho squared. All right, so it's kind of like we're working from right to left, but still, in most cases, it comes down to the bounds and make these problems easy or difficult. All right, so we know that the bounds for the innermost integral are, and I'll just kind of bring it in a little bit, z equals the square root of 18 minus x squared minus y squared. So we're going to do a few different things there, but I think it makes the most sense to get it into a recognizable standard form. So I'm going to square both sides. Z squared is equal to 18 minus x squared minus y squared. So add everything to the same side except for the constant. So x squared plus y squared plus z squared is going to be equal to 18. That should seem fairly familiar, all right, because that's a measure of rho, right, or at least a relationship that involves rho. So rho squared is equal to 18, making rho equal to the root of 18. All right. Now, we don't have a diagram here, but we could, suppose. We're looking at a sphere, and that sphere needs to be bounded on two ends. So we know that one end is going to be bounded by rho equals the square root of 18. It's just, okay, well, what's the other end? Right? So if we're working inside out, rho is the radius, right? So rho is always going to be connected to the origin. So if we're going to propagate outward, then it's going to be unless there's a gap, and that would come through in some form of subtraction, we'd be looking at something along the lines of rho equal to 0 on the low end, unless we have some other reason to think that that's not the case. We'd be saying that this is going from rho equals 0 to rho equals 18, root 18, I should say. All right, so we got one set of bounds there. And we just need the rest. All right. So the z equals, now, and you got to remember, very important here, just because something's associated with a particular integral doesn't mean, in the rectangular form, doesn't mean it's going to be associated with the same integral in cylindrical or spherical coordinates, right? Because it's associated with z, but maybe that means that it'll be associated with rho versus phi versus theta. We don't know, all right? So we got to keep an open mind. All right, so I'm going to look at my second, go purple. My second bound, z equals the square root of x squared plus y squared. All right, so it really is a question of what we can do with that. Well, we'll take a look and see, with our set of formulas, what that kind of boils down to. All right, we could also just kind of put that aside. There's nothing wrong with that. You can kind of play it by ear and say, okay, well, let's take a look at everything else. The constant ones, there's only so much you could do with that. But if I look at, for example, the x equals the square root of 9 minus y squared, I can square, that's a circle. That's something easily recognizable. X squared is equal to 9 minus y squared. So x squared plus y squared is equal to 9. That's a circle with a radius of 3. All right, just draw a quick sketch over there. So if it's saying that I'm bounded between the y-axis, because that's x equals 0, so here's let me just make a note of that. X equals 0. And let me draw a circle. Bring it in. It was a positive square root, so it's the top half. It's bounded by x equals 0 and the circle, right? So it's got to be with x equals 0 as its leftmost value. So all of this stuff is out. And its topmost value has to be the circle, right? So that's fine. Now, we could also take into account that it must be bounded by y equals 0. So we have all that information, and y equals 3. All right, so we get that all in the same diagram here. So here's y equals 0. I'm sorry, y equals 3. And I'll get y equals 0 in here also. So bounded in between these two parallel lines, which is jotted down, y equals 3, y equals 0. So to the right of x equals 0, above y equals 0, below y equals 3, and capped off with the circular function x equals the square root of 9 minus x squared, that's going to eliminate this piece and really just kind of get us going over here. So it's this base region that we're concerned with. All right, so that's helpful. All right, because in terms of, you're just thinking cylindrical coordinates, spherical coordinates, the one commonality is the theta. So that's telling me that my theta values should go from, based on what I'm seeing here, 0 to pi over 2. So theta equals 0, and it would go up to this location. It's going to work its way around. Theta equals pi over 2. All right, so I got my theta bounds, and it looks like I got my rho bounds. The only thing I'm missing is my phi. Why did I kind of skip over the z equals the square root of x squared plus y squared? I don't know. It just looked like this was easier to work with. I just went after what seemed to make sense first. All right. Also, something to keep in mind, the xy coordinate plane, I've been working with that for years. So something involving the xy plane should be easy to kind of visualize. So you may want to go after it that way. Just a thought. Anyway, yeah, so now the elephant in the room, the z equals the square root of x squared plus y squared. Well, we have a relationship for z. Let me get red involved here. Here's my z. Z is equivalent to rho cosine phi. And we also have a relationship, I'm going to go orange, for those keeping score at home, for the square root of x squared plus y squared. That's this guy over here. I'm just going to box the whole thing. Square root of x squared plus y squared is equivalent to rho sine of phi. All right. So we could bring everything over to the same side. So rho cosine phi minus rho sine of phi equals 0. Now this will confirm one of the suspicions from earlier, so it doesn't end up being hand waving, it ends up being more like, all right, it's justified algebraically. Factor out a row, you have cosine of phi minus sine of phi equals 0. It's quadratic in nature, product of two first degree expressions. So rho equals 0. So that confirms this theory. So we're good there. And then cosine of phi minus sine of phi is equal to 0. That's unit circle related, because what that's telling me is that cosine of phi is going to be equal to the sine of phi. And I'd be thinking, going around the unit circle, where does that happen? It happens in a couple of places, but if I'm looking at, heartburn. If I'm looking at just one turn around the circle, my possibilities would be phi is equal to pi over 4 and 5 pi over 4. All right. Now, 5 pi over 4, if you were to actually diagram that out, because remember, the phi is the angle, the angular movement from the z-axis. All right. So pi over 4 is 45 degrees away. Generally we want the shortest value of phi. Right. So that's the one we would probably go with, because if we're spanning outward from the z-axis, we're going to start off at 0 and span through to the value, that first phi value. All right. But if you were to consider, the nature of the situation, you'd say, okay, well, what is really 5 pi over 4? It's just another pi radians away from the pi over 4. All right. So what I would question or ask is that value relevant, number one? And number two, would it get picked up? Would that location get picked up through other rotations? All right, through other movements, through integration. All right. So we're looking at something, again, that's spanning outward from rho equals 0 to rho equals radical 18. So that's the radius. All right. So it's increasing in size. All right. It's also simultaneously, and you can kind of sort of develop the visual. I'll just do a rough sketch of it right here. It's going to be very rough. As in, good luck trying to interpret what I'm drawing. No, I'm just kidding. So, like, that was rough. So, we have our angle increasing through this interval to pi over 4, while also our radius is increasing. So, as I'm drawing the line, you got to kind of imagine the length is growing, right, until it gets to radical 18. All right, and then the last part is really just talking about it spinning, kind of rotating through an angle of pi over 2. So it's really going to be this line segment as it's growing upward, kind of like a lightsaber extending. As it's extending and moving out and covering that field, it's also making a quarter turn movement. So every point is getting spun a quarter of a turn around the axis. Well, not necessarily around the axis. It all depends on where you're going, but in this case, it's around the axis. So I'd probably give it a little bit more perspective. So in a way, it's going to be sort of conical. Yeah, maybe I wasn't wrong when I said good luck. Good luck trying to interpret my diagram. I'm going to give it one more honest effort. All right, I'll just do a little dashed line here to represent. All right, so again, it's spanning outward from the z-axis. It's growing up in length, and it's being spun. All right, so 3 variables at work at the same time. All right, so pretty tricky stuff. Now, the one thing that I don't think would necessarily be meaningful would be that 5 pi over 4, because 5 pi over 4, if you were to just kind of extend this line segment downward into this direction, that's going to put you below the xy plane. Right? That's not necessary. That's not needed, because when we're trying to find the volume here, it's the volume between the surface and the xy plane. So it's going to give you more than you need. So in fact, if you come up with anything for phi that's more than 90 degrees, then that's going to put you below the plane. If that's not explicitly called for in the problem, then you would disregard it. So we don't need this guy. We would want the pi over 4. So in terms of our integral, we would say it's a double integral going from 0 to pi over 2 for the thetas, going from 0 to pi over 4 for the phi. Then we're going from 0 to pi over 18, not pi over 18, I just like saying pi over stuff, that apparently is the key there. So root 18 of rho squared times rho squared sine phi d rho d phi d theta. And again, whatever you get out of that is going to be a whole lot easier to compute than it would be if you had to work with the x squared, y squared, z squared added and all those crazy bounds. All right. So that's really all we had to do is convert it into spherical coordinates. You know, it's kind of implied that maybe you go the distance, but it wasn't explicitly stated, so we leave it there. All right. So that was number 1 on page 87.